So there are two ways we know how far away stars are. The first one of those is parallax, which just uses triangles. So we can see we kind of have a top view on the sun, the earth, and one star here. And let's say that this is the middle of summer and it is right in the morning. We can see that we'll be able to look up in the sky and sort of see where that star is. That lets us draw a line to it. And there's a lot of angles here that we can record, this angle or this angle compared to the sun. And we take that first measurement of that star's location in the sky. So we also take a second measurement of that star's location in the sky, but we have to wait 6 months to do that, towards the middle of winter, and the Earth is on the other side of the sun. And that lets us look at the position that the star is in again. And this time we looked at it in the morning last time, we'll look at it at night, and we'll see where that star is and how its position has changed. So the way that lets us tell if that star's position has changed is easiest to see if we compare it to another star. So let's put a star a little bit closer to Earth. And this is going to be our red star here. Okay, so if we do the same thing with the red star, we'll see that that angle changed a lot more. It flipped way more from one side of the Earth to the other because that star is closer, even though we looked at it the same way. If we look at a star that's further away, we'll see that the angle or its position in the sky changes less. So when we look at the purple star, that angle changed less. Okay, so it was pointed to the left, and now it's a little bit to the right. With a red star, it changed a ton. So we can see how far away stars are by seeing how much their position changes in the sky when we wait 6 months. Now, this doesn't work for everything. In fact, if we have a star that's really far away, so let's shrink down our solar system here, make the night sky black again. If we have a star that's really far away, so let's make a blue star now, then that change is going to be even smaller, looking at it from two places. And you can imagine that if we keep going with this, with stars that get further and further away, these lines are going to get kind of flatter. They're going to make a flatter and flatter triangle. So let's do that one more time for a star that's even further away, because all of these are actually super duper close. So let's do that. We'll make our night sky black again. Maybe. And let's do a brown star, because believe it or not, there are brown stars out there. And we're going to make it, this is going to be our furthest away one. And you'll see that that line, those two lines looking at it from Earth, are even closer and closer. So that lets us tell how far away the stars are. Now there's some more complicated math and trigonometry that we can use to see exactly how far away that star is. But once a star gets further away than about half of our galaxy away, our instruments just aren't sensitive enough to tell the difference of the star's position in the sky. Eventually they just seem like they don't move at all. So parallax can only tell us the difference of stars that are relatively close. It can't tell us the distance of stars that are in other galaxies. And so we needed somebody working and analyzing data, and a scientist named Miss Leavitt came along and solved that problem for us. And we'll look at that in our next way that we tell the distance of stars and galaxies from Earth.